Okay, here we go again. This is the ISS. This is the ISS in space. Any questions? Well, I didn't get a lot of questions, but I sure got a lot of but assertions, like this one from Robert LaFleur. What do you think is the difference between 0 torr, 10 to the negative 3 torr, and 10 to the negative 17 torr? Millions of times almost zero is still almost zero. And Ruhiff asserts the difference between 1 psi and a very small fraction of that is just 1 psi, not a big differential. The question now is whether or not those assertions are accurate. And all you need to know that they aren't is this chart from Wikipedia and a little common sense. Dropping the pressure from 760 torr at sea level all the way to 25 torr can be achieved with rudimentary equipment. That's a difference of 735 torrs, a decrease of 97%, or going from 15 psi all the way down to half of a psi, with a rudimentary pump like the one invented in 1654 by Otto von Guericke. But Ruhiff and Robert LaFleur are asserting that the difference between 1 psi and 0 psi is virtually nothing. Here we're only talking about going from half of a psi to 0 psi. Surely we could just increase the power of von Guericke's 17th century pump a measly 3% and create a perfect vacuum, right? But that's not how it works. And you don't even have to be an expert in vacuum to understand this. Like I repeatedly told Ruhiff, all you really need is this chart. If going from half of a psi to 0 is really virtually nothing like they say, then why on earth would that tiny difference be divided into 6 distinct categories? Why would it involve high-tech multi-stage pumping devices and many other special conditions? Why would 0 psi be unachievable in any lab? After all, we're only talking about a difference of half of a psi, which is virtually nothing, right? It took 200 years to go from Otto von Guericke's rudimentary low vacuum pump that could achieve 30 torrs to Heinrich Geissler's medium pump that could achieve a tenth of a torr. That's 200 years to achieve a differential of virtually nothing. Another 165 years later, and we're now able to go from virtually nothing to, well, virtually nothing. So after 365 years of scientific ingenuity, we've been able to move through 5 of the 6 distinct categories of vacuum that, in total, define a difference of virtually nothing. And we did that by inventing a bunch of high-tech pumps and other equipment and procedures. Again, from Wiki. Several types of pumps may be used in sequence or in parallel. In a typical pump-down sequence, a positive displacement pump would be used to remove most of the gas from a chamber, starting from atmospheric pressure all the way down to 25 torr. That's the level von Guericke achieved with his rudimentary equipment. Then, a sorption pump would be used to bring the pressure down to 10 to the negative 4 torr. A cryopump, or turbomolecular pump, would be used to bring the pressure further down to 10 to the negative 8 torr. An additional ion pump can be started below 10 to the negative 6 torr to remove gases like helium or hydrogen. Boy, there sure are a lot of different kinds of extremely high-tech pumps involved in going from virtually nothing to virtually nothing, eh? But it's not just the high-tech pumps. Ultra-high vacuum generally requires custom-built equipment, strict operational procedures, and a fair amount of trial and error. Ultra-high vacuum systems are usually made of stainless steel with metal gasketed vacuum flanges. Stainless steel instead of very thin aluminum? Metal gaskets instead of rubber O-rings like on the control shafts of the ISS cupola, which haven't been replaced in 20 years? And are the only thing on those shafts standing between the vacuum of space and the pressurized ISS? Something's not adding up here, but the point is that going from 15 psi all the way down to half a psi is clearly a heck of a lot easier than going from that half a psi down to 0 psi. Summit Research builds high-end vacuum pumps and chambers. Their article, Understanding Vacuum, goes through many of their products and explains how better and better pumps are required to achieve deeper and deeper amounts of vacuum. It also highlights the special procedures, chambers, and other equipment required to achieve ultra-high vacuum. The author, who is an expert in the subject, writes, "Now take into consideration that negative 500 microns is not the opposite of 500 microns. If 0 to 500 microns is a gradient scale, we can assume at 0 microns we have established a unit of 1. So if you have negative 500 microns, it would be comparable to roughly 50 times 1. So if getting from 500 microns to 0 microns is a value of 1, getting to negative 500 microns would be considered 50 times or more the depth from 0. The wording is a little confusing, to be sure, especially since you can't literally have an area of space that contains a negative amount of microns, gas molecules, particles, atoms, or whatever. He's referring to how certain vacuum gauges are scaled. The deeper the vacuum, the farther into negative numbers the gauge reads. But once you know that, his point is easy to understand. He's basically saying that going from 2 psi to 1 psi is nowhere close to the same thing as going from 1 psi to 0 psi. According to Robert and Ruhiff's logic, if going from 500 microns to 0 takes X amount of power, then simply doubling the power will take you from 0 to negative 500 microns. But that's not how it works. As this expert points out, it would take in excess of 50 times more power. And then going from negative 500 microns to negative 1000 will take another 50 times more power, and so on. Going from 1 psi to 2 psi is not the opposite of going from 1 psi to 0 psi. Not even close. And we didn't even need a vacuum expert to tell us what is so obvious from this chart. If going from half a psi to 0 psi was really virtually nothing, there wouldn't be 6 different distinct categories between those 2 points. And there wouldn't be layers upon layers of ever more powerful pumps and special equipment and procedures to bridge a gap of virtually nothing. On the surface, going from 15 psi to 1 psi does seem like quite a bit more than going from 1 psi to 0 psi, mathematically speaking. But don't forget that, mathematically speaking, 10 to the negative 16 torr is 10 times the amount of pressure as 10 to the negative 17 torr. And 10 to the negative 15 torr is 10 times the amount of pressure as 10 to the negative 16 torr, and so on and so forth. So that should easily be enough to debunk Robert and Ruhiff's erroneous assertions. The only other rebuttal I got was that the aluminum walls of the soda can are thinner than the aluminum walls of the ISS. Of course, none of us can verify the wall thickness of something that we can't even verify exists in the first place. But let's take Don Pettit's claim that the ISS walls are 1/10 of an inch thick at face value for argument's sake. NASA's Space Power Facility in Ohio houses the largest and most powerful vacuum chamber on Earth. It can sustain a vacuum of 10 to the negative 6 torr, which, as we learned from Ruhiff, is virtually no different at all than the vacuum achieved by Otto van Guericke in 1654, right? The chamber itself is made out of aluminum, and according to Wiki, the floor plate and vertical shell are 1 inch thick, while the dome shell is 1 3/8 inches. So more than 10 times thicker than the ISS to withstand a much weaker vacuum. But wait, there's more. Even at over 1 inch thick, those aluminum walls aren't even close to strong enough. The entire aluminum chamber is encased in a concrete barrier that is 6 to 8 feet thick and is itself embedded with a leak-tight steel barrier. The ISS isn't encased in an 8-foot thick concrete barrier, is it? So while the walls of the ISS are purported to be thicker than the soda can, they're less than 1/10 as thick as NASA's vacuum chamber. And they don't have an 8-foot thick concrete and steel initial barrier separating them and the pressure inside of them from the 10 to the -9 torr vacuum of the thermosphere. I know this common sense information will resonate with those who have ears to hear, but I also know it will cause this reaction to those who don't.